Hello, so this is the video that talks about two-dimensional moments, right? And I'm going to introduce a way to do these problems that's definitely a lot faster, but it doesn't use the cross product method that Dr. O'Neill introduced in his video, because I think in terms of like a practical nature, I think yes, that was helpful in understanding how it's going to be used in 3D, but at the same time, I don't think it's that helpful in terms of time management on quizzes and exams. So I'll explain that in a second, but just know that this method is only valid for 2 dimensions. And the next video will talk about the methods for 3 dimensional moments. So essentially, this is the first time I'm sure a lot of you have heard about moments, especially if it is your first time taking the class. But a moment is essentially the tendency of a body to rotate if a force is applied to it. And my favorite example, because it's kind of the most common, like everyone has opened a door in their life. I'm fairly confident about that. So that's the example I'm going to use. So essentially, everyone knows that a door has a hinge and a handle, right? So the hinge is on this side in this case, and the handle is opposite the hinge, like all the way over here, right? So have you ever essentially considered why the handle is literally as far away from the hinge as it could be? It's because you don't have to push nearly as hard if you're pushing further away from the point of application, right? And there's several different examples of that we can go over if you want. And there's literally examples of this in all aspects of life and all interests. And if you want me to point out an example of a moment in your own context of your life, hit me up and I will absolutely point one out. But essentially, the door or the handle for the door is far away from the hinge because you won't have to push as hard. If you ever want to try this, go up to a door right now and try to push on it here. You're going to have to push much harder to get that door to pivot about that hinge because essentially the cross sectional or the perpendicular distance from the point of application of the force to the point of rotation of the door itself is so much smaller. So that's kind of what I wanted to talk about was this equation right here. So this equation is the two-dimensional moment equation, right? So it immediately relates the magnitude of the force or how hard you're essentially pushing on the door and the perpendicular distance between where you're pushing and where the door is rotating. So essentially the perpendicular distance of where you're pushing on the door to the hinge itself. So that makes sense then that if the door requires some moment for it to open, right? You would either have to push further away and lighter or increase the force and decrease the perpendicular distance. So if you were pushing at this point, you would end up having to push much harder to generate the same moment to open the door. Whereas if you were pushing at this point where you were designed to push it, you don't have to push nearly as hard because you're pushing further away. Same thing as if you are working out and there's this leg machine that works your thighs, right? Where you sit on that little chair, the bar goes on your lap, and then you kind of push this other thing up that rests on your ankles. They put that on your ankles because you're generating the largest moment about your knee, which requires the most activation of the thigh. So by loading your ankles in that situation, you end up lifting or exerting more force from your thighs, or not necessarily more force. You end up exerting um, more energy and within your muscle to generate the same moment because of that larger perpendicular distance. So I'm going to kind of talk about how to use this equation correctly um, because that's critical. So here's one of the examples, a variation of one of the examples that we're doing in class, right? So essentially there's this T-shaped thing, which is a fairly common structure in civil, I think. I don't really know, I'm bio. But essentially the question is find the overall moment about point A. So what do we know about a moment about something? So a door has a moment about its hinge. So what do we inherently know about the moment itself? The point that the moment is about does not rotate. It doesn't move, nothing. The door hinge stays in the same spot always, right? And everything moves about that point. Same thing when it says something about the moment about A, the point A doesn't move anywhere. So you can essentially think about in an exam kind of context, put your finger on point A and essentially drag the paper in the direction of whatever force and see how the page itself will rotate. And if you want me to go over that kind of example in person, it's kind of hard to explain that over a video on an iPad. But if you want me to go over that in person, please let me know and I absolutely will show you how I did that on exams. So I kind of wanted to go into this example a little bit, right? So the easiest way to think about it, right? And I'm going to rewrite our equation. So moment equals force times perpendicular distance. How many forces do I have here? Well, I have two, right? Technically, but how many of them have a relatively clear perpendicular distance? Really only the one at point C, right? The perpendicular distance between force C and point A would be the distance between the line of action. And so it'd essentially be this distance, right? Which is labeled as 12. So for the first point, I'm going to call it moment C. Actually, I should actually write moment C. So for a moment about generated by force C, it's that 5 pounds times that 12 inches, which is 1 foot, right? And then that would be 5 foot-pounds, right? But I have to have some sort of, so remember how when we were finding resultant forces, there was some kind of tug-of-war effect? Same thing when you have moments. Something will be pulling it one direction, something else could pull it another direction. So for that reason, you have to assign some kind of standard for what you're calling positive. I usually call clockwise positive. It doesn't matter as long as you're consistent. So looking at point C, is that force, that 5 pounds, going to pull this T clockwise or counterclockwise? And the way to think about it is if you pin it at A and pull point C to the left, the T is going to fall over to the right, which means that is going to essentially start to rotate clockwise. So in this case, the moment that's generated by force C is going to be positive. So now I have to look at the one at point B. So the moment at point B doesn't necessarily have a very clear perpendicular distance, because if I'm looking at the exact perpendicular distance of this, I have to extrapolate this line of action and then find whatever this distance is. That's the perpendicular for force B as it's drawn. But I could also break force B up into its two components, right? So there's some part that's pulling it down and some part that's pulling it to the left, right? So if I break it up into those components, it's a lot easier for me to find the perpendicular distances, right? So this is going to become Vy. This is going to become Vx. And then I forgot to draw this angle. We'll call it a 512 triangle, right? So that's going to incorporate actually some review, which is probably good. So we have this 5 foot-pounds. I'm just going to draw it as 5 instead of positive 5. So there's that. So that positive 5 foot-pounds we've already figured out. Let's start with Bx, right? So we have here the moment from Bx. So the first thing is to figure out how much of the force is in that x direction, right? So here we have that overall 6 pounds, right? And then it's scaled down by some factor, right? And by using this slope triangle here, this 12 and the 5, we can figure out exactly how much of that force goes in the x direction. So since it's a similar triangle, I can just relate the two sides. So the 5 part of that triangle is what describes the x direction because they're pointing in the same direction, essentially. They're parallel to each other. So that 6 pounds, if I multiply it by 5 over 13, where that 13 is the hypotenuse of the 5, 12, 13 triangle, I now have the magnitude of the force at point B going in the x direction. I then have to find the perpendicular distance. But since this Bx force is parallel to the moment C force, it's the same perpendicular distance. So this line of action extrapolates to here, and now this is the same perpendicular distance. It's that same 1 foot. Which then becomes, I don't exactly know. But is it positive or negative? If I fix point A, so if I pin point A down and pull the left side of the T to the left, that T is going to fall to the left or counterclockwise, which according to my convention up here should be negative. So that's going to be negative, whatever number that is, foot-pounds. So then I have to find MBY because this vertical component of that force also is generating some kind of rotation. So I know the magnitude is just going to be the opposite component of the one I just used. So it's going to be the 12 over 13 part. But now what's the perpendicular distance? I have to start using other colors. Hold on. So if I extrapolate this piece down to where A is, now this is my perpendicular distance. And this distance here is labeled above as this 6 inches. And 6 inches, converting that to feet, is 0.5 feet. So then I know that this is some number. I don't know the exact number because I didn't do this beforehand. And I don't want to waste your time with the calculator. So that's going to be some number foot-pounds. Again, let's test and see if it's positive or negative, right? If I fix it at point A and pull down at point B, this T is going to try to fall to the left a little bit. So again, it's going to be counterclockwise according to my convention, which is negative. So now if I'm going to find the overall moment generated at point A, I have to add all these together. So the total moment about A, calling clockwise positive, is the sum of all the other moments. So I have my 5 foot-pounds minus my whatever the BX one was, foot-pounds, minus the whatever the Y component caused. Then you're going to get some overall moment. I'm so sorry that this is like this. And let's just say, I have no idea if this is the correct number or not, but let's just say we got -3 foot-pounds. Okay? So -3 foot-pounds here. I don't know if O'Neill said this in both classes, but don't ever give a negative answer. Okay? So if I called clockwise positive and I got a negative answer, what should my answer actually be? My answer should actually be 3 foot-pounds, right? Magnitude, units, direction. So if this was my positive convention, I got a negative answer. It's the opposite of my convention. So then it's counterclockwise, right? And then where is it rotating about? That's important. So essentially you have to identify what your hinge is. So it's rotating about point A. This is what your overall answer should look like. So magnitude, units, direction, and then point of application or point of where it's rotating about. So again, if you guys have any questions, please reach out to me. This is essentially a carbon copy of what we're doing in class with different magnitudes of forces and different directions. So this is essentially the same layout. I just picked random arrows, so I didn't give you the exact answers. This is kind of my favorite example. So if you ever forget what a moment is or why that equation is what it is, think of a door. And if you have any questions, or like I said, if you want to see if we can point some kind of application in your everyday life or in your interests out, we absolutely can. Just text me and we can talk about it. All right, I will see you guys in class.